Imagine this: you are walking through a quiet, ancient library by candlelight. The shelves are endless, stacked with tomes that whisper the stories of life, one organ, one cell at a time. The room is hushed, and yet if you listen closely you can almost hear the rhythms of circulation, the exhale of breath, the soft electrical shimmer of thought. This is not a library of myth or magic. It is your own body, and tonight we are opening its pages together. Even as you drift toward sleep or sink into focused study, this journey will unfold slowly, layer by layer. Like the chapters of an atlas, we will trace the landscape of the human body from its smallest unit cells and tissues to the orchestrated complexity of entire systems. From the whisper of nerve signals to the strength of bone, from the delicate exchange of gases in the lungs to the quiet labor of the kidneys, each part will reveal its purpose in the larger whole. It begins with a single cell, the foundational unit of life. These microscopic structures, so small that thousands could fit on the head of a pin, are both ancient and astonishingly complex. Cells build tissues, tissues build organs, and organs form systems. But each level is more than the sum of its parts. Like starlight woven into a constellation, these structures align to create the living experience you inhabit. There is something soothing about this knowledge. To study anatomy is to ground oneself in the certainty of structure, the elegance of function. For the exam-worn medical student, the sleep-deprived nurse, the curious listener with a cup of tea in hand, these details form an architecture of understanding, a lantern in the dark, illuminating what it means to be alive. What makes the human body so quietly extraordinary is not just its strength or endurance, but its patience. Skin renews itself, bones adapt, neurons fire, rest, and fire again. Systems cooperate with such seamless precision that their orchestration is often invisible until it falters. But here, in this exploration, we will bring their harmony gently to light. Our path is deliberate, guided. We will begin with the cellular level, the molecular machinery, the compartments, the signals that pass like messages in a bottle. Then we will examine how tissues emerge from these units, specialized for protection, movement, signaling, and support. From there, we will build outward, exploring the skin that marks our boundary with the world, the bones and muscles that shape and move us, the blood that delivers oxygen and immune defense, the lungs that fill quietly with air, and the digestive and urinary systems that sustain and cleanse. We will wander the labyrinth of the brain and glands, the systems of control that monitor and adjust the body like an orchestra conductor, refining every note. We will revisit our first moments through embryology, glimpse the extraordinary variation of real-life anatomy, and pause to reflect on how this knowledge finds its way into clinics, surgeries, and technologies that extend our health and humanity. And as we go, we will marvel not just at the textbook facts, but at the poetic realities behind them. The heart beats roughly 100,000 times each day. The surface area of the lungs, when unfolded, could cover a tennis court. The intestines are home to trillions of microbes, each playing their part in digestion and immunity. These are not just statistics, they are quiet truths, humming beneath our awareness, holding us steady with every breath. In this exploration, sleep is not a hindrance, but a companion. The mind, even when drowsy, continues to absorb and connect. Like a sponge in warm water, it softens to new patterns. The rhythm of this script, the structure of these lessons, is designed to support that passive learning calm, consistent, and immersive. You do not need to memorize every detail as we pass. Instead, let the ideas settle gently. Let the metaphors guide you. The body as a city, with highways of arteries and signal lights of synapses, or as a garden with cells budding and blooming in harmony. These images, once planted, may linger longer than rote definitions, growing into understanding over time. We are not racing toward answers. We are walking through a cathedral of form and function, noticing the stained glass intricacies along the way. Inhale, exhale. The journey has already begun. The body waits, ready to be seen, system by system, with quiet awe. Imagine, for a moment, that you could become smaller, so small, in fact, that you pass between the fibers of your own shirt, through the pores of your skin, and into the microcosmic world that lies within your feet, but instead a dynamic membrane. Towers of protein rise and fall like machinery on a factory floor. All around you, microscopic sacs ripple with energy. You have entered the domain of the cell, the smallest living unit of the human body, and the first true chapter in the anatomy of life. A human body contains roughly 37 trillion cells. These tiny compartments, each surrounded by a thin, semi-permeable membrane, form the structural and functional building blocks of tissues, organs, and systems. Yet, within each one lies an entire world in miniature, self-sustaining universe that breathes, communicates, reproduces, and repairs. At its simplest, a cell is enclosed by a plasma membrane, a delicate yet purposeful boundary, composed mainly of a phospholipid bilayer. What enters and exits the cell? It acts as both gatekeeper and guardian, allowing nutrients in, permitting waste out, and maintaining internal stability, or homeostasis. Embedded within this membrane are proteins that act like channels, receptors, and signals, each one part of a continuous conversation between the cell and its environment. Step inside, and we find cytoplasm, the gelatinous fluid that fills the cell's interior. Suspended within it are organelles, each performing a specific task. Think of them as the instruments in an orchestra or the departments within a company, each with a specialized role that contributes to the cell's life. At the center of most cells lies the nucleus, often described as the control center. It houses DNA, the genetic material arranged into structures called chromosomes. DNA is more than just a code. It is the master blueprint for all the proteins the body requires. Wrapped tightly and protected within the nuclear envelope, it unspools only when needed, transcribed into RNA, which then travels to the cytoplasm to guide protein assembly. Among the most essential organelles is the mitochondrion, often dubbed the powerhouse of the cell. But this is more than just a metaphor. Mitochondria performs cellular respiration, a process that converts glucose and oxygen into adenosine triphosphate, or a Tapestries energy currency that powers almost all cellular activities. Imagine chemical reactions like tiny bonfires, controlled, efficient, and ongoing, releasing the energy that fuels muscle contraction, nerve transmission, and even quiet thought. In a single human cell, there may be hundreds to thousands of mitochondria, depending on the tissue's energy demand. For example, cardiac muscle cells, which never rest, are rich in mitochondria, while skin cells may contain fewer. These organelles have their own DNA, hinting at their evolutionary origins as once independent organisms, now seamlessly integrated into human life. Surrounding the nucleus and mitochondria, other organelles lend their services. Exists in two forms, rough and smooth. The rough studied with ribosomes is where proteins are synthesized assembled from amino acids like beads on a string. The smooth lacks ribosomes but plays vital roles in lipid synthesis, detoxification, and calcium storage. Once synthesized, proteins travel to the Golgi apparatus, a stacked membranous structure that modifies, sorts, and packages them for delivery. Think of it as a cellular post office, ensuring each molecule reaches the right destination inside or outside the cell. Other components include lysosomes, which digest cellular waste, and peroxisomes, which neutralize toxins. Even the cytoskeleton, composed of microfilaments and microtubules, plays a role in maintaining cell shape, enabling movement, and anchoring organelles. Yet cells are not static. They grow, divide, and die, processes that mirror the cycles of life itself. The most fundamental of these is mitosis, the process by which a single cell divides to form two genetically identical daughter cells. Mitosis is central to growth, healing, and cellular turnover. Each day, millions of skin, blood, and intestinal cells are replaced through this tightly regulated process. Its precision is extraordinary. The cell must duplicate its DNA, align its chromosomes, and evenly split its contents, all while maintaining the integrity of its function. But not all cells are destined for duplication. Stem cells, however, are uniquely equipped for both self-renewal and differentiation, the ability to develop into specialized cell types. Embryonic stem cells can become nearly any cell in the body, from neurons to muscle fibers, while adult stem cells are more limited but still vital, especially in tissues like bone marrow and skin. They lie at the heart of regenerative medicine, with the potential to repair damaged tissues or even grow replacement organs. Their presence in the adult body provides a reservoir for healing, and their manipulation in laboratories opens new frontiers in treating diseases from leukemia to Parkinson's. Despite their diversity, immune share this common architecture, this molecular toolkit. Their internal environments may differ, but the core machinery is conserved. This unifying structure allows cells to specialize while still speaking a common biochemical language. PATHWA's complex networks of proteins and molecules that respond to stimuli and regulate behavior. For example, in response to injury, signaling cascades can instruct a cell to divide, migrate, or secrete healing factors. Communication can be local between adjacent cells or distant, mediated by hormones carried in the bloodstream. Even in rest, a cell is never truly still. Proteins are continuously produced and degraded. Organelles move along microtubule tracks, and ions flow in and out, maintaining voltage differences across membranes. Neurons, for instance, rely on such electrical gradients to transmit impulses, tiny voltage shifts that result in thought, perception, and motion. Understanding the cell is like understanding a seed. From the zygote, the single cell formed at conception, to the fully developed human body. This cellular machinery repeats and refines itself, generation after generation. In every breath we take, every step we walk, and every wound we heal, cellular processes unfold quietly and faithfully. They knit flesh from protein, generate thought from ions, and power motion from glucose. They are the quiet artisans of the human experience, unseen yet indispensable. And now, from this cellular foundation, we are ready to step outward to see how these microscopic units combine to form the tissues that shape our bodies. Just as individual notes become a melody, so too do cells become the living architecture of form. Let us turn now to that next layer of complexity. Picture the human body not as a machine, but as a finely woven tapestry, threaded together, not with cotton or silk, but with living strands of cellular fabric. Every surface, every contour, every internal structure is made not from steel or stone, but from tissue arrangements of cells, bound by function and form. As we leave the microscopic world of the single cell behind, we now enter the realm of tissues, the next order of life's quiet architecture. Tissues are groups of similar cells working together toward a common goal. They provide structure, protect delicate areas, send messages, and generate movement. The human body contains 4 primary tissue types: epithelial, connective, muscle, and nervous. Each one is distinct in its role, but together they form the living fabric of anatomy, an intricate loom where the warp and weft of biology are drawn tight. Let us begin with epithelial tissue, smooth, cellular covering that defines the boundaries between our inner selves and the outside world. Epithelia line every exposed surface, the skin, the inner lining of the digestive tract, the airways of the lungs, and the blood vessels that trace through our organs. Imagine tiles on a floor or shingles on a rooftop, layered, organized, protective. Epithelial tissue can be simple, with a single cell layer, or stratified, with multiple layers. It may be flat, squamous, cube-shaped, cuboidal, or columnar, depending on its location and function. In the lungs, thin squamous cells enable gas exchange. In the intestines, tall columnar cells absorb nutrients. These layers are anchored to a basement membrane, a thin scaffold that connects epithelium to the tissues below. But epithelial cells do more than cover. Many specialize to secrete substances forming glands that produce sweat, saliva, hormones, or enzymes. Others bear tiny cilia, like brushes that sweep mucus and debris from the respiratory tract. And still others form tight junctions, sealing gaps to prevent leakage between cells. Epithelia are constantly renewed, especially in areas subject to friction, like the skin or stomach lining. Here, stem cells divide, push upward, and are eventually shed like leaves falling from a tree. Beneath and between epithelial layers, we encounter connective tissue, perhaps the most diverse and expansive of the tissue families. Connective tissues provide support, anchor organs, store energy, and transport materials. Unlike which are densely packed, connective tissues contain fewer cells and more extracellular matrixa, mixture of fibers and ground substance that defines their texture and strength. Some connective tissues are soft and pliable. Loose connective tissue fills spaces between organs, cushions, blood vessels, and supports epithelial layers. It contains fibroblasts, which produce collagen and elastin proteins that give the tissue its resilience and stretch. Adipose tissue, or body fat, stores energy in the form of lipid droplets and insulates the body against heat loss. Other connective tissues are firmer. Dense connective tissue forms the ligaments and tendons that link bones and muscles. These are rich in tightly packed collagen fibers, aligned like ropes under tension. Cartilage, a semi-rigid form, cushions, joints, and shapes the nose, ears, and trachea. It contains chondrocytes, cells that reside in small chambers called lacunae, surrounded by a smooth, rubbery matrix. At its strongest extreme, connective tissue becomes bone, or osseous tissue. Bone is mineralized, giving it strength and rigidity. It contains osteocytes, cells housed within concentric rings of calcium matrix, much like the rings of a tree. Despite its hardness, bone is alive, remodeled constantly through the actions of bone-forming osteoblasts and bone-resorbing osteoclasts. Circulating through all these tissues is yet another form of connective tissue, blood. Though it seems fluid and transient, blood meets the criteria of connective tissue. It contains cells, red blood cells, white blood cells, and platelets suspended in a matrix called plasma. Blood transports oxygen, nutrients, hormones, and waste. It also serves as the medium for immune defense and clotting. Next, we turn to muscle tissue, the engine of movement. Muscle is unique among the tissues for its ability to contract, producing force and motion. The body contains three types: skeletal, cardiac, and smooth. Skeletal muscle attaches to bones and enables voluntary movement. Under the microscope, it appears striated, banded, due to the organized arrangement of contractile proteins. Skeletal muscle fibers are long, cylindrical, and multinucleated. They respond to signals from the nervous system with rapid, powerful contractions. Cardiac muscle, found only in the heart, is also striated, but differs in that its cells are branched and interconnected by structures called intercalated discs. These discs allow electrical signals to pass swiftly between cells, ensuring the heart contracts in a coordinated, rhythmic beat roughly 100,000 times per day across a lifetime. Smooth muscle, as its name implies, lacks striations. It lines the walls of hollow organs, blood vessels, intestines, the bladder, and contracts involuntarily, moving blood, food, or waste through internal pathways. Smooth muscle fibers are spindle-shaped and function with endurance rather than speed, often maintaining tone for long periods without fatigue. Finally, we reach nervous tissue, the body's information network. Composed of neurons and glial cells, nervous tissue detects stimuli, processes information, and initiates responses. A neuron consists of a cell body, branching dendrites that receive signals, and a long axon that sends impulses over long distances, sometimes more than a meter in length. Neurons communicate through synapses, tiny gaps where chemical messengers, called neurotransmitters, bridge the space between cells. Surrounding the neurons are glial cells, supportive cells that nourish, insulate, and protect the neural network. In the brain, glia outnumber neurons roughly 10 to 1, forming a silent but essential scaffolding for thought. To see tissues clearly, one must often turn to the microscope. In histology, the study of tissues, glass slides reveal cellular arrangements, like miniature landscapes, layers of cells, like bricks in a wall. fibrous networks like spider webs or waves of muscle bundled like braided rope, stained with dyes like hematoxylin and eosin. These slices come alive in color, revealing nuclei, cytoplasm, and matrix. Understanding tissues is to understand the vocabulary of the body's construction. Each organ is a sentence built from these 4 tissue types, arranged and emphasized to match function with form. The skin, for instance, combines epithelial protection, connective support, nervous detection, and smooth muscle control. The intestine weaves together absorption, movement, and immune defense in a single, fluid motion. Tissues are the threshold between the microscopic and the visible, the place where cells take on form and purpose. From this layer, we move now to the first true system, to the skin, the body's largest organ, and its barrier to the world. Let us trace its contours and understand how it both shelters and senses the world around us. Imagine the body as a planet. Beneath its surface lie rivers of blood, forests of muscle, and networks of electricity. But before we reach any of that, we pass through the atmosphere, thin, dynamic, protective, in the human body. This atmosphere is the integumentary system, the skin, hair, nails, glands, and the fine biochemical veil that surrounds us. It is our first defense, our last boundary, and our constant signal to the world. Skin is not just a covering. It is the largest organ of the human body, spanning about 2 square meters and weighing around 4 to 5 kilograms in an average adult. Despite its thinness often no thicker than a few millimeters, it is layered with purpose and rich in complexity. Like the layers of a forest canopy, each stratum of the skin performs essential, overlapping tasks. The outermost layer is the epidermis, a thin barrier composed mostly of keratinocytes, cells that produce the protective protein keratin. These cells originate in the basal layer, where stem cells divide and push older cells upward. As they rise, keratinocytes die, harden, and become flattened, forming the stratum corneum, a dead but vital shield. This layer is constantly sloughing off and renewing, a quiet cycle of loss and regeneration that takes roughly a month. Beneath the epidermis lies the dermis, a thicker, living layer, rich in connective tissue, blood vessels, nerve endings, and glands. Here we find collagen for strength, elastin for flexibility, and a web of capillaries that help regulate temperature and nourish nearby cells. Within this terrain lie sweat glands, sebaceous glands that secrete oil, and hair follicles rooted like wells into deeper structures. Deeper still, the hypodermis, or subcutaneous tissue, consists largely of adipose tissue fat that insulates the body and cushions internal organs. This layer connects the skin to underlying muscles and bones, anchoring it while also allowing for movement and flexibility. But the skin's role extends far beyond structure. It is an active gatekeeper of the body's thermal, immunological, and communicative needs. Through thermoregulation, the skin helps maintain internal temperature. When heat rises, eccrine sweat glands secrete fluid that evaporates from the surface, cooling the body. In colder conditions, blood vessels constrict, limiting heat loss. From the skin's surface, the skin also acts as an immune sentry. Langerhans cells, found in the epidermis, patrol for foreign invaders and alert the immune system to potential threats. The skin's surface hosts a microbiome diverse community of bacteria, fungi, and viruses, that compete with pathogens and support skin health. These microscopic inhabitants vary by region, moisture level, and even by individual, forming an invisible mosaic of protective life. Color is another language of the skin. It arises largely from melanin, a pigment produced by melanocytes found in the basal layer of the epidermis. Melanin absorbs ultraviolet radiation and shields DNA from its damaging effects. The amount and type of melanin eumelanin, brown-black, or pheomelanin red-yellow, determines skin tone. Contrary to popular belief, people of all skin colors have roughly the same number of melanocytes. It is their activity and the granule size that vary. Skin color reflects not just genetics, but evolutionary adaptation. In equatorial regions, darker skin protects against intense UV radiation, reducing the risk of folate depletion and skin cancer. In colder climates with lower sunlight, lighter skin permits more efficient vitamin D synthesis, essential for bone health. Thus, the skin is a living record of ancestral geography, climate, and migration. Consider a surprising case in high-altitude communities of the Andes or Himalayas. Skin often darkens, not from genetics alone, but from persistent UV exposure at altitude, despite cold temperatures. In contrast, Inuit populations in Arctic regions traditionally maintain sufficient vitamin D not through skin exposure, but through a diet rich in fish and seal, evidence that biology and culture adapt in tandem. The skin also communicates subtly, but constantly. Blushing, for example, occurs when blood vessels in the dermis dilate, a response modulated by emotional states like embarrassment or attraction. Paleness, flushing, jaundice, and cyanosis are visual cues that reveal internal conditions: anemia, fever, liver dysfunction, or lack of oxygen. Through skin, the invisible becomes visible. Pathologies of the skin remind us of its vulnerability. Psoriasis, an autoimmune condition, accelerates skin cell turnover, leading to inflamed, scaly patches. Vitiligo causes melanocytes to disappear in certain areas, resulting in depigmented patches. And in cases like eczema, the skin's barrier becomes inflamed and hypersensitive, reacting to irritants with discomfort and visible change. Climate and environment shape the skin's secret economy in other ways. In arid regions, sebaceous glands may overproduce oil in an effort to prevent moisture loss. In humid settings, fungal infections become more common due to persistent dampness. Occupational exposures, such as in farming, mining, or industrial work, can leave marks that persist across a lifetime. Calluses, sunspots, chemical burns. Hair and nails, both part of the integumentary system, are composed primarily of keratin. Hair follicles originate deep in the dermis and grow outward, influenced by hormones and nutrition. Hair insulates, protects, and in animals can serve for camouflage or warning. In humans, its role is more nuanced, social, cultural, and historical. Nails protect the tips of fingers and toes, enhance tactile sensitivity, and serve as indicators of health. Changes in nail color or texture can signal underlying systemic issues. In every sense, the integumentary system is both sentinel and storyteller. It shields the internal world, senses the external one, and mirrors our internal state quietly, persistently. Every freckle and scar, every fine hair and goosebump speaks of the skin's role as a dynamic interface between the self and the world. And so, beneath this living veil, we find the machinery that powers it all: muscle, bone, and the framework that gives the body motion and form. Let us now descend deeper to the skeleton and the sinews that allow us to stand, reach, and move through space. Picture a coral reef beneath the waves, delicate yet durable, teeming with life, constantly built up and broken down by unseen forces. Now imagine that structure living within you, not beneath the sea, but deep under skin and sinew. This is your skeleton, a scaffold of bone that is not dead stone, but living, responsive, tissue growing, reshaping, and quietly adapting to every movement you make. The human skeleton, in its adult form, consists of 206 bones. Each one is part of a greater architecture, forming a dynamic system that supports the body, protects vital organs, stores minerals like calcium and phosphate, and houses the marrow that produces blood. But bones are far more than rigid supports. They are active participants in motion and metabolism structures shaped by time, tension, and use. At the cellular level, bones are governed by a quiet choreography between two key types of cells. Osteoblasts build bone. They secrete a matrix of collagen and other proteins, then mineralize it with calcium phosphate to create hardened tissue. Osteoclasts, by contrast, break bone down. They dissolve minerals and clear out damaged or unneeded tissue. Together, they perform a lifelong balancing act known as bone remodeling, a cycle of renewal that replaces roughly 10% of our skeleton every year. This remodeling is not random. It responds to pressure. Where muscles tug, bones grow thicker. Where stress is absent, they thin. This principle, known as Wolff's Law, explains why astronauts who spend months in microgravity can lose significant bone mass unless they exercise regularly in space. Without the constant pull of gravity, the osteoblasts grow quiet and the skeleton begins to atrophy. Now imagine the structure of a single bone, perhaps the femur, the thigh bone, the longest in the human body. Externally, it appears solid, but inside, it contains two main types of tissue. The outer layer is compact bone, dense and strong, organized into repeating units called ostens, which resemble the growth rings of a tree trunk. Inside lies spongy bone or trabecular bone, a lighter lattice-like tissue that allows for strength with minimal weight. This inner network also houses bone marrow, which comes in two forms: red marrow, responsible for producing red blood cells, white cells, and platelets, and yellow marrow, rich in fat and energy reserves. Bones are connected at joints, or articulations, places where motion is made possible by structure. Some joints, like those in the skull, are immovable. Others, like the shoulder and hip, are synovial joints, surrounded by capsules of fluid that reduce friction and allow a wide range of motion. Within these joints, ligament bands of fibrous connective tissue hold bones together, while tendons connect muscle to bone, enabling movement when muscles contract. Muscles, in turn, act as biological motors. They pull, never push, always, working in pairs or groups to create motion. When a muscle shortens or contracts, it pulls on the tendon, which moves the attached bone. This system of muscles and bones operates on principles of mechanical physics, specifically the use of levers. In anatomical terms, a lever is formed by a bone, the rigid bar, a joint, the fulcrum, and the force generated by muscle contraction, Different types of levers exist in the body. In a classic first-class lever, like the neck balancing the head, the fulcrum sits between the effort and the load. A second-class lever, as seen when standing on tiptoe, places the load between the fulcrum and the effort. The most common type, third-class levers, such as the biceps lifting the forearm, have the effort between the load and the fulcrum. These levers favor speed and range of motion over brute strength, allowing for the fine control that characterizes human movement. Beneath this system lies a subtler sense proprioception, often called the sixth sense. This is the body's ability to sense its own position, movement, and tension without looking. Proprioceptors, specialized sensory receptors found in muscles, tendons, and joints, feed a constant stream of information to the brain. Without them, even simple acts like walking or holding a pen would require conscious visual effort. It is proprioception that allows dancers to move with eyes closed and athletes to adapt mid-stride to uneven ground. To better understand how bones and muscles respond to stress, consider the case of Kenyan distance runners, many of whom hail from the high-altitude region of the Rift Valley. Decades of scientific observation have shown that these athletes often possess a unique combination of long, slender lower limbs, low body mass, and dense yet lightweight bones. Their efficiency arises not only from genetics and training, but from the adaptive shaping of their musculoskeletal system in response to lifelong running, first as children running to school, then as competitors striding across continents. Contrast this with astronauts in orbit. Deprived of weight-bearing activity, they face bone density losses of up to 1% per month. Calcium leaches from their bones, increasing the risk of fractures. Muscle mass also shrinks, particularly in postural muscles that normally resist gravity. To combat this, space agencies require astronauts to follow rigorous resistance training protocols, even in microgravity. When they return to Earth, they must retrain their muscles and rebalance their bones, sometimes relearning how to walk. Clinical snapshots also illustrate how fragile and dynamic this framework can be. In osteoporosis, bone becomes porous and brittle, a silent condition often unnoticed until a fracture occurs. It disproportionately affects postmenopausal women due to shifts in hormone levels that influence calcium absorption and bone maintenance. Preventative strategies include weight-bearing, exercise, adequate intake of calcium and vitamin D, and medications that regulate the activity of osteoblasts. In contrast, conditions like muscular dystrophy, group of genetic disorders, show how muscles themselves can falter. In Duchenne muscular dystrophy, for instance, the absence of a key protein causes muscle fibers to break down over time, leading to progressive weakness and eventual loss of mobility. Even when the skeletal structure is intact, the absence of functional muscle renders the system inert. There is a poetic paradox here. The bones and muscles, so strong and enabling, are also sensitive to neglect, disuse, and imbalance. A sedentary lifestyle can shrink muscles and weaken bones just as surely as malnutrition or disease. Yet this very responsiveness offers a kind of hope. The system listens to tension, to use to effort, and reshapes itself accordingly. Invites participation. Movement becomes a message. Stretch, reach, stride. Lifting the body answers by adapting. The musculoskeletal system, then, is not a static scaffold, but a symphony of cooperation. It speaks in calcium and collagen, responds to strain with strength, and dances between movement and stillness. It is the framework of life in motion, responsive and alive. Now, with motion in mind, we turn to the control center that guides it all, the nervous system. A forest of neurons, a river of signals. Let us enter the circuitry of thought, sensation, and command. Imagine tracing the journey of a single red blood cell, tiny biconcave disc, just 7 micrometers across. It slips through capillaries so narrow it must fold itself to pass. It moves silently but with purpose, carried by a force greater than itself, within a river that never rests. This river is blood, warm, rhythmic, and astonishingly complex. Alongside it flows another, quieter stream, the lymph, which gathers what blood leaves behind, filters it, and defends its borders. Together, blood and lymph form the circulatory and lymphatic systems, a pair of interwoven highways and checkpoints, essential not only for survival, but for balance, repair, and memory. At the center of this network is the heart. About the size of a clenched fist, the human heart beats over 100,000 times a day, pumping nearly 7,500 liters of blood. It has 4 chambers to atria and 2 ventricles, 4 valves that direct flow with the precision of clockwork, the tricuspid, pulmonary, mitral, and aortic valves. These valves open and close in perfect sequence, producing the familiar lub-dub of each heartbeat. Blood flows through 2 main circuits: the pulmonary circuit, which sends blood to the lungs for oxygenation, and the systemic circuit, which delivers oxygenated blood to every tissue in the body. Now, let us follow a single erythrocyte, or red blood cell, as it begins its loop. It leaves the left ventricle of the heart via the aorta, the body's largest artery. This cell carries oxygen, bound tightly to hemagglutinin, iron-rich protein that gives blood its red color as it travels through arteries, arterioles, and finally, capillaries. The oxygen is released into tissues, fueling metabolism, motion, and thought. After delivering its oxygen, the erythrocyte begins its return journey through venules and veins. It enters the superior or inferior vena cava, depending on its origin, and flows into the right atrium. From there, it moves into the right ventricle, which pumps it through the pulmonary artery to the lungs. In the lungs, carbon dioxide is exchanged for fresh oxygen, and the cycle begins anew. But this red cell does not travel alone. Suspended in plasma, pale yellow fluid, composed mostly of water, are white blood cells, platelets, electrolytes, hormones, nutrients, and waste products. Each has its role in the maintenance of life. White blood cells, or leukocytes, are the guardians of the body, defending against invaders like bacteria, viruses, and parasites. Some, like neutrophils, act quickly and in large numbers, engulfing pathogens. Others, like lymphocytes, provide longer-term immunity, remembering past infections and preparing for future encounters. There are about 5 liters of blood in the average adult body, and every drop is filtered and monitored. This surveillance is supported by the lymphatic system, a parallel network of vessels, nodes, and organs. Unlike blood, lymph doesn't circulate in a closed loop. It begins in the interstitial spaces between cells, where fluid leaks from capillaries. This fluid is collected by lymphatic capillaries and slowly moved through lymph nodes, small bean-shaped organs that filter debris and house immune cells. The spleen, too, plays a vital role. It filters blood, recycles old erythrocytes, and stores white blood cells. Meanwhile, the thymus, nestled above the heart, is where T lymphocytes mature, a process vital during early life. The flow of blood is driven by the pumping of the heart, but veins require assistance. Unlike arteries, veins have thinner walls and less muscular tones. They rely on skeletal muscle contraction and one-way valves to move blood upward against gravity. This is why a long period of stillness, such as sitting during a flight, can lead to pooling of blood and even deep vein thrombosis, a dangerous clotting condition. Specialized structures called venous reservoirs, such as those in the liver, spleen, and skin, can store large volumes of blood and release it when needed, such as during hemorrhage or intense physical exertion. These reservoirs are part of the body's strategy for volume control, maintaining homeostasis even under stress. As blood passes through the coronary arteries, it nourishes the heart itself. These arteries branch off the aorta just after it leaves the heart and wrap around the heart muscle like a crown, hence the name coronary. Blockage of these arteries, such as in a myocardial infarction or heart attack, deprives the cardiac muscle of oxygen. Without rapid intervention, the muscle dies, impairing the heart's ability to pump. Historically, humanity has tried to read the body through the rhythm of this circulation. In Ayurveda, the ancient Indian system of medicine, pulse diagnosis Purexia involves subtle palpation of the radial artery to infer imbalances in the body's energies or Practitioners train for years to detect changes in rhythm, strength, and character. In traditional Chinese medicine, the pulse is analyzed in multiple positions along the wrist, each corresponding to a different organ system. Modern medicine, too, has elevated pulse to a diagnostic tool. Telemetry, the remote monitoring of vital signs, allows clinicians to observe heart rate, blood pressure, and oxygen saturation from afar. Devices like smartwatches can detect arrhythmias such as atrial fibrillation or heartbeat patterns that may otherwise go unnoticed. The pulse, once felt by fingers on a wrist, is now digitized, analyzed, and monitored continuously, forming part of the expanding field of digital health. Yet, despite all this complexity, the circulatory system remains beautifully efficient. A single red blood cell completes its journey through the body in about 60 seconds. Over its 120-day lifespan, it travels the equivalent of 2 trips around the globe, powered by nothing more than pressure gradients and molecular diffusion. Even more remarkable is blood's role in memory, not cognitive memory, but immunological memory, the record of battles fought once a pathogen has been encountered. Specific white blood cells, memory B cells, and memory T cells in the bloodstream, ready to respond faster and more effectively upon re-exposure. This is the principle behind vaccines. Train the immune system using a harmless mimic so that real threats are neutralized quickly. In disease, these rivers can falter. Anemia, caused by a deficiency of red blood cells or hemoglobin, leads to fatigue and pallor. Leukemia, a cancer of white blood cells, overwhelms the marrow's ability to produce healthy blood. Lymphedema, often following cancer surgery, causes swelling due to poor lymph drainage. Each condition reveals the delicate balance required to keep these flows intact. The circulatory and lymphatic systems are not isolated. They integrate with every other system, feeding the brain, cleansing the skin, powering the muscles, transporting hormones from glands to targets. They are highways of life, defense, and renewal. Consider that at this moment, billions of cells move within you unseen, tireless, interconnected. They carry oxygen to the fingertips, ferry waste from the toes. Recall the virus from last winter and heal the paper cut on your hand. They circulate not randomly, but with purpose, guided by valves, rhythms, and gradients, orchestrated by the heart and refined by countless generations of evolution. These rivers do more than sustain, they unite. A single bloodstream nourishes the entire human organism, linking the skull to the souls, the brain to the bones, the present to the past. It is through this circulation that body and memory flow as one. And now, having followed the red cell's loop, we turn to the great conductor of these flows, the nervous system, the spinal cord, the brain. Let us now enter the forest of the mind, where thought becomes impulse and sensation becomes motion. Pause for a moment and take a breath. What seems like a simple act, the quiet rise of the chest, the subtle swell of the abdomen is, in fact, one of the most elegant and continuous dances in the body. It begins as air enters the nostrils, a wind gliding past tiny hairs and mucus-lined walls that warm, moisten, and filter the invisible mixture of gases we call air. From here, the air enters the nasal cavity, where turbulent flow allows particles and microbes to be trapped. It passes through the pharynx, shared with the digestive tract, then descends into the larynx, the voice box. Folds of tissue, like harp strings, can vibrate to produce sound. Now the air flows into the trachea, a tube held open by C-shaped rings of cartilage. In the passive learning mind, you might picture the trachea as a hollow flute, resonating with each inhalation, narrowing and branching as it descends. The trachea splits into the right and left primary bronchi, each entering a lung and branching further into secondary and tertiary bronchi, like the roots of an upside-down tree. These bronchi narrow further into bronchioles, then into terminal bronchioles, and finally, the journey reaches its destination, the alveoli. Each alveolus is a tiny air sac, just 200 micrometers across. There are approximately 480 million alveoli in a pair of human lungs, and their combined surface area, about 70 square meters, is roughly the size of a tennis court. They cluster like grapes, delicate yet resilient, surrounded by a lacework of pulmonary capillaries. It is here, in these alveolar gardens, that the miracle of gas exchange occurs. The alveolar walls are only a single cell thick. Oxygen diffuses across this barrier into the red blood cells flowing through the capillaries, binding to hemoglobin with quiet urgency. At the same time, carbon dioxide, a waste product of cellular respiration, diffuses from the blood into the alveoli to be exhaled. This process is governed by partial pressures. Oxygen moves from areas of high concentration in the air to lower concentration in the blood. Carbon dioxide flows in the opposite direction. No energy is required, only the passive, beautiful logic of physics. This quiet exchange occurs approximately 12 to 16 times per minute in adults, more during exertion, less during sleep. And yet, despite its constant rhythm, respiration is more than just chemistry and mechanics. It is exquisitely tuned to the demands of the body and deeply intertwined with emotion, thought, and adaptation. Consider the phenomenon of chemoreception. Specialized receptors in the medulla oblongata aortic bodies and carotid bodies detect changes in carbon dioxide and pH levels in the blood. When carbon dioxide rises or pH drops, these sensors send signals to increase the respiratory rate. In contrast, a fall in carbon dioxide can trigger a slowing of breath or even apnea. The diaphragm, a dome-shaped sheet of muscle separating the thoracic and abdominal cavities, is the primary driver of breathing. During inhalation, it contracts and flattens, expanding the lungs and drawing air in. The intercostal muscles between the ribs assist by raising the ribcage. Exhalation at rest is usually passive recoil of tissues, a gentle fall. But in moments of exertion, breath becomes more forceful. Accessory muscles in the neck, chest, and abdomen join in, pushing the limits of expansion and compression. Even the lungs themselves are not identical. The right lung has 3 lobes, the left only 2 to make room for the heart. Now consider the adaptability of this system, particularly in response to extreme environments. At high altitudes, such as the Andean Plateau or the Tibetan Plateaus, above 3,500 meters, the air is thinner, with less oxygen available per breath. Andean populations, who have lived at altitude for millennia, tend to have larger chest cavities and increased hemoglobin concentrations. Their bodies produce more red blood cells, allowing for greater oxygen carrying capacity, albeit with thicker blood. In contrast, Tibetan highlanders show a different strategy. Rather than increasing hemoglobin, their bodies enhance ventilation and nitric oxide production, which dilates blood vessels and improves oxygen delivery. Their adaptation focuses on efficient oxygen use rather than sheer volume. And then there are freedivers, who dive to astonishing depths on a single breath. With training, they slow their heart rates, conserve oxygen, and override the normal urge to breathe, triggered by rising carbon dioxide levels. Some can hold their breath for over 10 minutes. Their lungs can compress without damage. Their spleens release extra red blood cells, and their minds enter a calm, trance-like state, testament to human plasticity. Breathing is also a bridge between the voluntary and involuntary systems. Most of the time, it occurs automatically, yet we can take conscious control at will, deepening, slowing, or holding it through practices such as pranayama in yoga, qigong, or modern breathwork. People have long explored the influence of breathing on emotion, physiology, and mental clarity. In sleep, breathing becomes more regular, often slower. The brain regulates it through circuits in the pons and medulla, fine-tuning the depth and rhythm without our awareness. Yet, conditions like sleep apnea, which breathing stops momentarily, remind us how vulnerable this rhythm can be. Diseases of the respiratory system, such as asthma, chronic obstructive pulmonary disease, the delicate nature of airflow and exchange. In asthma, the bronchioles constrict and inflame, obstructing airflow. In COPD, the alveolar walls break down, reducing surface area and making gas exchange inefficient. In pneumonia, alveoli fill with fluid, preventing oxygen from reaching the bloodstream. Each condition reminds us that breath is not guaranteed. It is earned, moment to moment, by a system of remarkable elegance. The respiratory system also plays a subtle role in speech, olfaction, and pH regulation. Exhaled air is shaped by the tongue, lips, and vocal cords into words. The nasal passages detect thousands of chemical compounds, enabling the sense of smell. And by adjusting the level of carbon dioxide in the blood, respiration helps maintain the body's pH within a narrow, essential range. Imagine now a foggy morning. You stand quietly, your breath rising in the cool air. With every inhalation, you draw in the atmosphere oxygen made by forests, oceans, and phytoplankton. With every exhalation, you return carbon dioxide to the world, nourishing plants in return. You are part of a global exchange, an unbroken cycle linking lungs to leaves, cells to seasons. And so we conclude our journey through the alveolar gardens and return to the rhythmic rise and fall of the chest. The breath is not just air, it is exchange, connection, and renewal. As we leave the airways behind, the next path winds deeper inward into the electric forest of nerves and networks that sense, move, and remember. From gas to signal, from breath to thought, we now step into the nervous system. Digestion begins long before food reaches the stomach. Sometimes it starts before a single bite is taken. The mere sight or scent of a favorite meal, baking bread, ripe mango, simmering stew can trigger salivation. This anticipatory reflex, known as the cephalic phase of digestion, is the body's way of preparing. The brain, sensing that nourishment is near, sends signals to the salivary glands, stomach, pancreas, and intestines to ready their secretions. Enzymes stir, acids rise. The digestive orchestra tunes itself for the coming performance. The first act takes place in the mouth. Here, saliva, rich in water, enzymes, and mucins, begins the transformation. The enzyme amylase starts breaking down starch into smaller sugars. Lingual lipase prepares to act on fats, though its full activity will emerge later in the stomach. Meanwhile, the act of mastication, chewing, mechanically grinds food, increasing surface area for enzymatic action. This physical and chemical blending produces a soft, slippery mass called a bolus. Swallowing or deglutition is both voluntary and involuntary. It begins with conscious motion, but soon surrenders to reflex. The bolus slides past the epiglottis, which folds down like a gentle gate to shield the airway, and enters the esophagus. Through a series of rhythmic contractions called peristalsis, the esophagus escorts the bolus downward toward the stomach, a hollow muscular organ shaped like a pouch or crescent moon. Its walls are layered with muscles and lined with glands that secrete gastric juice, a potent mixture of hydrochloric acid and pepsinogen. The acid unfolds proteins. Pepsinogen, activated into pepsin, begins digesting them. This phase is not just breakdown, it is containment and timing. The stomach churns the food into a semi-liquid substance called chyme, then releases it gradually into the small intestine, a winding tube about 6 meters long. It is herein the duodenum, jejunum, and ileum that true absorption begins. The chyme receives bile from the liver and gallbladder, which emulsifies fats, breaking them into microscopic droplets. It also encounters pancreatic juice, rich in enzymes like lipase, amylase, and proteases, targeted to a specific nutrient group. The enzymes act in parallel, digesting lipids, carbohydrates, and proteins into their absorbable units, fatty acids, monosaccharides, amino acids. The inner lining of the small intestine is a masterpiece of surface area. Like a plush carpet, it is covered with millions of villi-finger-like projections that increase the absorptive interface. Each villus is further coated with microvilli, forming what is known as the brush border. This border is more than structure. It contains enzymes and transporters that finalize digestion and begin absorption. Imagine the villi reading your meal like Braille, decoding its structure, sensing its chemistry, and extracting nutrients with precision. Glucose is taken up through active transport, escorted into the bloodstream. Fatty acids are reassembled into chylomicrons and carried into the lymphatic system. Amino acids diffuse into capillaries. Vitamins, minerals, water all find their paths. But the body is not alone in this process. Within the intestines live trillions of microbes, vast and intricate microbiome composed of bacteria, fungi, viruses, and archaea. These organisms help digest fibers that human enzymes cannot, producing short-chain fatty acids that nourish the gut lining. They synthesize vitamins, such as vitamin K and biotin, modulate the immune system, and influence mood and metabolism. Each person's microbiome is unique, shaped by genetics, geography, and perhaps most deeply by diet. Consider fermented foods across cultures. In Korea, kimchi is spicy. Fermented cabbage dish contains lactobacillus species that support gut health. In Ethiopia, injera, a sour flatbread made from teff flour, is teeming with wild yeasts and lactic acid bacteria. In Eastern Europe, kefir offers a symbiotic blend of bacteria and yeast in a fermented milk drink. Each food is not merely nutrition, it is a living community, a continuation of microbial coevolution. The relationship between humans and microbes is older than history. Some researchers suggest that the ability to digest lactose persistence evolved in certain populations due to the long-term consumption of dairy. Others link seaweed digestion in Japanese populations to microbial genes acquired from traditional diets rich in nori. The microbiome, then, is not simply a guest, it is a collaborator, a resident alchemist helping to transform food into fuel, tissue, and thought. As nutrients are absorbed, they enter the hepatic portal vein, which leads directly to the liver, the body's metabolic command center. The liver filters and processes these nutrients, deciding which to store, convert, or send onward. It regulates blood glucose levels, detoxifies harmful substances, synthesizes proteins, and produces cholesterol and bile. What remains of digestion now enters the large intestine, or colon. Here, water and electrolytes are reabsorbed. The microbiome continues to ferment undigested material, producing gases and vitamins. The colon compacts waste into feces to be stored in the rectum and expelled through the anus in a final act of elimination. Yet even this is not a mere byproduct, it is diagnostic. Changes in stool, color, texture, or frequency can signal disorders ranging from celiac disease to colon cancer. The digestive tract is a mirror of health, constantly reflecting the internal state. There is something profoundly intimate about digestion. What we eat becomes us literally. It is how the outside world becomes inner matter, how the harvest becomes muscle, enzyme, and memory. It is also a dialogue between us and our food, between our cells and our microbes, between culture and chemistry. Shared meals pass down knowledge, shape microbiota, and forge connections across generations. From the enzymes in saliva to the whispered signals between gut bacteria and brain cells, digestion is a slow, continuous alchemy. It nourishes not just the body, but the self. And so, from the winding loops of the intestines, we move next to a different kind of communication, one that rides electrical impulses rather than molecules, and signals meaning faster than thought. The nervous system awaits a web of light and motion, linking all that comes next. Imagine the body as a vast inland sea, its waters renewed each moment by unseen tributaries. Whatever we drink, whatever our cells release, eventually joins an ever-moving current of plasma. Somewhere deep inside, two silent guardians stand. Watch over this tide, the kidneys bin-shaped, fist-sized, and tirelessly precise. From the final coils of the intestines, nutrient-rich blood flows into the liver for inspection, then returns to the general circulation. Now, its solutes must be balanced, its acids and bases tuned, its wastes quietly removed. That is the calling of the urinary system, the kidneys, ureters, bladder, and urethra organs that filter, refine, and release. Each kidney nests just below, the ribs cushioned in fat and anchored against the posterior abdominal wall. Inside lies a world as intricate as a coral reef, roughly 1 million nephrons, the microscopic filtering units. A nephron begins with a tuft of capillaries called the glomerulus, housed within a cup-shaped Bowman's capsule. Here, blood pressure drives plasma across a porous membrane, creating a filtrate that resembles blood without its cells or large proteins. This filtrate enters the renal tubule, winding through the proximal convoluted segment, the loop of Henle, and the distal convoluted segment before reaching the collecting duct. Along this path, water and solutes are selectively reclaimed, sodium, chloride, glucose, amino acids pulled back in silence, urea, creatinine, excess acids allowed to pass. By the time the fluid leaves the collecting duct, it has become urine, a mere 1% of the original filtrate, yet dense with unwanted residues. Regulation here is constant and multi-layered. When blood pressure falls, specialized cells near the glomerulus release renin, initiating the renin-angiotensin cascade that constricts vessels and signals the adrenal cortex to secrete aldosterone, prompting nephrons to retain sodium and water. When plasma osmolarity creeps up even by a few milliosmoles in the hypothalamus fire, inducing thirst and prompting the posterior pituitary to release antidiuretic hormone, ADH renders collecting ducts permeable to water, allowing more to be reabsorbed. Urine darkens, volumes shrink, and balance is restored. This dance of hormones is so finely tuned that an athlete running on a cool morning might excrete pale, dilute urine, while the same athlete on a hot afternoon may conserve nearly every droplet, producing only a trickle of concentrated amber. Across Earth's deserts, adaptations push this efficiency to extremes. The kangaroo rat survives without drinking liquid water at all. Its kidneys extend the loop of Henle into deep medullary regions, reclaiming nearly every molecule. Among humans, desert nomads, such as the Bedouin, display remarkable fluid economy, a heightened sensitivity to thirst signals, sweat glands that activate late to minimize evaporative loss, and cultural practices like traveling at dawn that align behavior with physiology. Yet the kidneys do more than manage water. They guard the body's acid-based balance, excreting hydrogen ions and reabsorbing bicarbonate, keeping blood pH within the narrow corridor of 7.35–745. They produce erythropoietin, a hormone that stimulates red blood cell formation, and convert vitamin D to its active form, calcitriol, essential for calcium absorption. When these midnight custodians falter, the consequences ripple outward. Chronic kidney disease, CKD, affects nearly 10% of the global population, often driven by diabetes and hypertension conditions that damage the delicate glomerular vessels. In some agricultural regions of Central America, South Asia, and Africa, a mysterious form called CKD of unknown origin strikes young field workers, possibly linked to heat stress, dehydration, and agrochemicals. Without early detection, CKD progresses silently until toxins accumulate, causing fatigue, edema, and deranged electrolytes. At that stage, dialysis or transplantation may be the only lifelines. Dialysis, which routes blood through an external filter, or peritoneal dialysis, which uses the belly's own membranex as an artificial kidney. Yet treatments are time-consuming, costly, and emotionally taxing. Access is uneven. While urban hospitals may offer thrice-weekly sessions, rural patients often travel great distances or go without. Global health advocates call this the quiet crisis of nephrology, an epidemic overshadowed by more visible diseases yet deeply entwined with poverty, climate, and diet. Prevention begins upstream, controlling blood pressure, moderating salt, staying hydrated, and screening at risk individuals. Simple dipstick tests can detect proteinuria, early sign of damage long before symptoms appear. Education programs teach agricultural workers to rest in shade and drink liberally, combating heat-related injury. In labs, researchers explore regenerative therapies, coaxing stem cells toward nephron-like structures in hopes of future implants. While we sleep, our kidneys continue their vigilant patrol, filtering about 180 liters of plasma each day, reclaiming nearly all but one. They clear metabolic ashes from cellular fires, adjust the chemistry of the blood, and, through subtle hormonal whispers, script the feeling of thirst that nudges us toward a glass of water. In the hush of night, when breath slows and heart rate softens, these organs hum with quiet purpose, draining, balancing, safeguarding. From these cleansing streams, we rise to a system yet subtler, a realm of sparks and chemical letters where neurons flash and hormones drift, coordinating mood, growth, and memory across the human landscape. It is time to enter the channels of signals and secret messages. Beneath the surface of skin and bone, deep in the unseen architecture of the body, two great signaling systems guide us. One flashes in pulses of electricity, the other drifts in tides of molecules. Together, they form a communication network, as intricate as a coral reef, as fast as lightning, and as subtle as a shift in moonlight. The nervous and endocrine systems are the body's master messengers, delivering commands, warnings, and whispers to cells near and far. Imagine neurons firing in the brain like bioluminescent plankton, tiny bursts of light in a vast ocean. Each flash is a message, sent from one cell to another through a carefully orchestrated series of steps. This is the nervous system, fast, precise, and electrically charged. Beside it flows the endocrine systems, lower, but no less powerful. It releases hormones, chemical messengers carried in the bloodstream, drifting like sealed letters in bottled glass. These two systems overlap and interweave. Let us begin with the neuron, Phi's fundamental unit of the nervous system. A neuron is a specialized cell with a long, branching structure, a cell body housing the nucleus, dendrites receiving input, and a slender axon transmitting the signal. At rest, the inside of the neuron holds a negative electrical charge compared to the outside. This difference, called the resting membrane potential, is maintained by ion channels and pumps, particularly the sodium-potassium pump, which exchanges 3 sodium ions for 2 potassium ions with each cycle. When a neuron is stimulated past a threshold, it fires an action potential, rapid change in voltage that travels like a wave down the axon. This electrical signal is not unlike a spark running along a wire. At the axon terminal, the message encounters a synapse, a tiny gap between neurons. Here, the electrical impulse transforms into a chemical one. Neurotransmitters, such as dopamine, serotonin, or acetylcholine, are released into the synaptic cleft. These molecules bind to receptors on the next neuron, altering its membrane potential and possibly triggering a new action potential. This leap across the synapse may take mere milliseconds, but it is the foundation of every thought, movement, emotion, and sensation. Neural pathways grow and shift over time. During development, the brain creates far more synaptic connections than it will ultimately keep through a process known as synaptic pruning. Connections that are unused or inefficient are eliminated, allowing the brain to refine itself. This is most active in childhood and adolescence, but continues into adulthood. Like a gardener trimming branches for healthy growth, the nervous system sculpts its own circuitry. While neurons carry messages quickly and locally, hormones travel slower and farther, produced by endocrine glands such as the pituitary, thyroid, adrenal glands, pancreas, and gonads. Hormones influence tissues across the body. A single hormone molecule may linger in the blood for minutes or hours, its presence felt long after its release. Consider adrenaline, also called epinephrine, secreted by the adrenal medulla during acute stress. It is the signature hormone of the fight-or-flight response. Heart rate climbs, pupils dilate, airways open. Blood is diverted from the skin and digestive organs toward muscles. Glucose floods the bloodstream, fueling action. All this can happen in seconds, triggered by a perceived threat, be it a charging animal, an oncoming car, or an unexpected sound. But the endocrine system is also responsible for the long arcs of life. Growth hormone, released by the anterior pituitary, helps regulate height and tissue repair. Thyroxine, produced by the thyroid, maintains the body's metabolic rate. Insulin and glucagon from the pancreas orchestrate the fine balance of blood sugar. Estrogen, testosterone, and progesterone coordinate reproductive cycles, bone density, and mood. These messengers do not operate in isolation. The hypothalamus, a small region at the base of the brain, acts as a conductor between the nervous and endocrine systems. It receives neural inputs about the body's status temperature, light, hydration, and responds by sending releasing hormones to the pituitary gland. The pituitary, in turn, dispatches signals to other endocrine glands, adjusting their output. In a feedback loop, feedback is essential. Most endocrine systems operate through negative feedback, a process where rising levels of a hormone inhibit its further release, maintaining balance. For example, as cortisol levels rise during stress, they eventually signal the hypothalamus and pituitary to reduce further secretion. This keeps hormone levels within a functional range. Yet this finely tuned orchestra can be disrupted. Endocrine disruptors are synthetic or natural compounds that interfere with hormone signaling, found in pesticides, plastics like BPA, and certain pharmaceuticals. These chemicals may mimic, block, or alter hormone production. In wildlife, exposure to endocrine disruptors has led to reproductive abnormalities in fish and amphibians. In humans, links have been drawn to decreased sperm counts, early puberty, thyroid issues, and metabolic disorders. Mood, too, is deeply intertwined with signaling. Serotonin, often associated with well-being, is influenced by diet, sunlight, and stress. Dopamine, involved in reward and motivation, can be shaped by behavior, addiction, and neurochemical balance. In depression, anxiety, and schizophrenia, disruptions in these systems produce profound effects, reminding us that emotion is not abstract but biological. Memory offers another glimpse into the union of signal and self. As neurons fire in patterns, certain pathways are strengthened through repetition, a process called long-term potentiation. Structural changes at the synapse solidify memory traces. Hormones also influence memory. Cortisol, at moderate levels, can sharpen recall. At high levels, such as during chronic stress, it can impair it. In rare neurological conditions, these connections falter. In Alzheimer's disease, for example, neural circuits are disrupted by amyloid plaques and tau tangles. The result is progressive memory loss, disorientation, and altered personality. These symptoms reveal how fragile the web of signaling truly is, how a subtle imbalance in biochemistry can reshape identity itself. Despite its complexity, the body's signaling network remains beautifully integrated. A smell can trigger a memory can shift heart rate, a shift in posture can change hormone levels. The systems speak to each other, constantly flashing, drifting, responding. Consider the enteric nervous system, sometimes called the second brain, embedded in the walls of the gastrointestinal tract. With over 100 million neurons, it operates independently yet communicates with the brain through the vagus nerve. Its messages influence mood, hunger, and immunity. The gut microbiome, too, plays a role producing neurotransmitters and modulating inflammation. This gut-brain axis reminds us that thought, digestion, and emotion are intimately bound. In every waking moment and in dreams, these signals continue, whispering, firing, ebbing, and flowing. The brain generates about 20 watts of electrical power at rest, enough to light a small bulb. Yet it does not burn out. It adapts, prunes, repairs, and evolves, shaped by experience and environment. From the first flutter of a fetal heartbeat to the last breath, the body is governed by these messages, silent flashes and drifting letters. They carry not only information but intention, the blueprint of movement, memory, and being. As we turn now from communication to defense, from coordination to protection, we enter the realm of the silent shield, a system that learns, remembers, and sometimes misfires, guarding the self from the unseen world. Before breath, before heartbeat, before form, there is the zygote, a single cell suspended in fluid silence, containing all the potential of a human life. From this point, a biological symphony begins, unfolding with astonishing precision and grace. Embryology, the study of this unfolding, reveals how the body first comes into being. It is a story of division and differentiation, of hidden shapes emerging like time-lapse petals of a lotus. The journey begins at conception, when a sperm cell fuses with an egg, forming the zygote, a cell with a full set of chromosomes, half from each parent. This cell divides within hours, first into 2, then 4, then 8. These early divisions occur without growth, forming a cluster of cells called a morula, named for its resemblance to a mulberry. Within a few days, the morula becomes a blastocyst, a hollow sphere with an inner cell mass that will give rise to the embryo itself. Soon after implantation into the uterine wall, the inner cell mass undergoes a process called gastrulation, the point at which symmetry is broken. This is when the embryo transforms from a uniform sphere into a layered structure, each layer destined to form different tissues. These 3 layers are the ectoderm, mesoderm, and endoderm. The ectoderm, the outermost layer, will give rise to the nervous system and skin. The mesoderm in the middle forms muscle, bone, the heart, and blood. The endoderm, deepest within, becomes the lining of the gut, lungs, and internal organs. From this simple layering, all complexity arises. By the 3rd week of development, a structure called the notochord forms along the embryo's midline. This rod of mesodermal cells acts as a signal center, triggering the development of the neural tube from the ectoderm above. The neural tube will become the brain and spinal cord. If this tube fails to close properly, it can result in conditions like spina bifida or anencephaly. At the same time, the heart begins as a simple tube that loops and folds, eventually giving rise to a 4-chambered pump. By day 22, the embryonic heart begins to beat well before limbs have formed or the brain has fully taken shape. Blood vessels sprout and branch, like roots seeking connection, nourishing the rapidly growing tissues. Somites spared blocks of mesoderm line the developing neural tube. These will become the vertebrae, ribs, and skeletal muscles. The limbs appear as tiny buds by the 4th week, with fingers and toes emerging in the 6th. Eyes and ears take shape. The face, once a flat sheet of tissue, folds and fuses into recognizable contours. Around the 7th week, sexual differentiation begins. Initially, all embryos possess the same undifferentiated gonadal ridge. In the presence of the SRY gene on the Y chromosome, this ridge becomes testes. Without it, it develops into ovaries. Hormonal signals then guide the formation of internal and external genitalia. Male and female anatomy diverges, but the origins remain strikingly symmetrical, a testament to the shared blueprint underlying human diversity. The fetus continues to grow and refine its form. The bones harden, the lungs branch into intricate airways, the brain folds into gyri and sulci, increasing its surface area. By the end of the 1st trimester, many organ systems are formed. The second and third trimesters bring maturation, fat storage, and practice breathing movements, swallowing, and even REM sleep. Yet, while embryology illuminates how the body forms, reproductive anatomy reveals the structures through which this process is supported and sustained. The female reproductive system includes the ovaries, where eggs develop and hormones like estrogen and progesterone are produced. Each month, an egg is released during ovulation and travels down the fallopian tube, where it may encounter sperm and become fertilized. The fertilized egg, or zygote, then moves toward the uterus, a muscular organ with a nutrient-rich lining, ready to host the developing embryo. The male reproductive system includes the testes, which produce sperm and testosterone. Sperm mature in the epididymis, travel through the vas deferens, and mix with fluids from the seminal vesicles and prostate gland to form semen. When these systems work in concert, conception may occur naturally. But many couples require assistance to age, medical conditions, or unexplained infertility. Assisted reproductive technologies have evolved dramatically over the past decades. In vitro fertilization, IVF, for example, allows eggs to be fertilized outside the body before being implanted in the uterus. Pre-implantation genetic testing enables the selection of embryos without inherited disorders. These advances, once the realm of science fiction, are now routine parts of fertility medicine. Still, the process of pregnancy and birth remains deeply tied to ancient knowledge. Across cultures, midwives have long guided labor using herbal remedies, touch, and breath. In traditional Ethiopian villages, women give birth in low stone-walled huts known as maternity houses, surrounded by female kin. In Japan, Shinto rituals bless both mother and child before and after delivery. In Mexico, birth attendants use techniques passed down through generations, blending indigenous and modern wisdom. These practices underscore a truth often missed in clinical settings. Birth is not only biological, but social and spiritual. It is the moment where private origins become shared presence, where potential becomes person. The embryo's journey from a single cell to a breathing infant mirrors, in miniature, the entire arc of development. It is at once ordinary and astonishing happening. Every moment somewhere on Earth, yet shaped by forces honed over millions of years of evolution. Embryology, then, is not just the study of beginnings. It is the study of transformation, of how form follows signal, and how cells, with no eyes to see or hands to shape, arrange themselves into symmetry and complexity. As we now move from the womb to the immune system, we encounter another mystery: how a body defines what is self and what is not. Just as the embryo must distinguish tissues to form organs, the immune system must distinguish friend from foe, building a memory of invaders, and sometimes, tragically, turning against its own. We now cross into the quiet vigilance of the silent shield. The human body, for all its elegant engineering, is not without its curiosities. Beneath its symmetrical surface, there are quirksome, rare mindeths, some surprisingly common, that remind us evolution is not a designer, but a tinkerer. It works with what already exists, adapting, looping, repurposing. And sometimes the result is strange, beautiful, or deeply revealing. Let us begin with situs inversessa, rare condition where the major visceral organs are mirrored from their normal positions. In this reversal, the heart is found on the right side of the chest instead of the left. The liver, normally on the right, sits to the left. The stomach and spleen swap sides too. Remarkably, most people with this condition live completely normal lives. It affects approximately 1 in 10,000 people and often goes undiagnosed unless medical imaging is performed for unrelated reasons. This reversal occurs during embryonic development, when the cilia, tiny hair-like structures, fail to direct the usual left-right asymmetry cues. In a more severe form, known as Cardiovascular syndrome, situs inversus is accompanied by respiratory problems and infertility due to defective cilia elsewhere in the body. The existence of situs inversus tells us that while symmetry is typical, it is not always essential. Our organs are not randomly placed, but neither are they so fragile that a flipped configuration must fail. It speaks to the resilience built into biology. Now consider supernumerary ribs, scries, usually arising from the cervical spine in the neck. These are called cervical ribs, and they occur in about 1 in 200 people. Many never notice them. But in some cases, these extra ribs compress nerves or blood vessels, leading to a condition called thoracic outlet syndrome, with symptoms like pain, numbness, or weakness in the arms. The presence of extra ribs is an echo of our evolutionary past. Earlier vertebrates, including reptiles, had longer rib-bearing segments along their spines. Humans retain the genetic blueprint for this, and sometimes the old pattern reemerges. Similarly, we sometimes encounter supernumerary nipples appearing along the so-called milk linen embryonic ridge that stretches from the armpits to the groin. While humans typically develop only a pair of breasts, other mammals, like dogs and pigs, form multiple bells. When this ancestral pattern partially persists in humans, it creates a harmless extra nipple. About 1 in 18 people have one, often mistaken for a mole. Then there are the rare connective tissue marvels, like Ehlers-Danlos syndrome, a group of genetic disorders affecting collagen. People with certain forms of this condition may have hyperelastic skin that stretches far beyond normal limits, or hypermobile joints that bend with unusual ease. The flexibility can appear almost superhuman, but it often comes with vulnerability, frequent joint dislocations, fragile skin, and poor wound healing. One striking example is the extensible skin seen in classical Ehlers-Danlos, where the dermis has less structural integrity. Though rare, such individuals offer insights into how much we rely on scaffolding proteins like collagen for daily function and protection. Another curiosity is polydactyly, the presence of extra fingers or toes. Sometimes the additional digit is fully formed and functional. In other cases, it's rudimentary. This condition affects around 1 in 500 live births. In some communities, it's viewed as a sign of uniqueness or even advantage, especially when the extra digit provides greater grip or dexterity. Now, let us follow a peculiar path deep inside the neck to a nerve that loops far longer than seems necessary. The recurrent laryngeal nerve, a branch of the vagus nerve, is responsible for controlling the muscles of the larynx, the voice box. On the right side of the body, it loops around the subclavian artery, but on the left, it makes an astonishing detour, descending into the chest to loop around the aortic arch before ascending back up to the larynx. This long, looping route is not efficient. If one were designing a human from scratch, surely a direct path would suffice. But this configuration is an artifact of evolution. In fish, where the heart lies close to the gills, the nerve takes a straightforward route. As vertebrates evolved and the neck elongated, the heart descended, and the nerve tethered to embryological structures was dragged along with it. It had no mechanism to shorten its path, so it looped. What was once a minor detour became, in the giraffe, a 15-foot-long loop to reach the larynx. This anatomical oddity, while functionally effective, is vulnerable. Damage to the recurrent laryngeal nerve can result in hoarseness, loss of voice, or difficulty swallowing. Surgeons operating in the neck, especially during thyroid surgery, must take great care not to injure it. Next, we turn to a curious vestige, the coccyx, or tailbone. This small, triangular bone at the base of the spine is all that remains of a tail. While no longer functional for balance or movement, it anchors pelvic muscles and ligaments. In very rare cases, children are born with a small vestigial tala benign protrusion of soft tissue that can be removed without complication. Such cases remind us of our shared ancestry with tailed primates and mammals. Some people also retain remnants of embryonic pathways that should have closed. For instance, the patent foramen ovale, a hole in the heart that normally seals after birth, persists in about 25% of adults. Most never know it, but in certain circumstances, it can allow blood to bypass the lungs, contributing to stroke or migraine. Then there are palmaris longus muscles, present in about 85% of people, absent in the rest. This slender muscle, running from the forearm to the palm, once helped with gripping and climbing. Today, it is functionally unnecessary and often harvested for surgical grafts. Its absence causes no impairment. Some quirks are not physical, but sensory. A small percentage of the population can taste PTC, bitter compound, so intensely that it seems toxic, while others find it tasteless. This variation reflects genetic differences in taste receptors, which evolved to protect early humans from poisonous plants. Bitter sensitivity, it turns out, is a relic of foraging. Others have tetrachromacy, a condition where usually a woman possesses a fourth type of cone cell in the eye, potentially allowing perception of millions more colors than the average person. While still debated, this heightened visual spectrum may give them subtle powers of color discrimination unnoticed by others. Variation, whether genetic or structural, is not just a source of anomaly, is a wellspring of adaptability. The very traits that might seem like flaws or curiosities may, in another context, confer advantage. Even rare mutations can drive discovery. For example, the study of congenital insensitivity to pain, a condition where individuals feel no physical pain, has advanced our understanding of nerve signaling and led to new analgesic research. Similarly, fibrodysplasia ossificans progressiva, where muscle turns to bone, has revealed secrets about skeletal development and repair. As we reflect on these wonders and quirks, we are reminded that the standard human form is but one variation among many. Each deviation offers a window into biology's breadth, to what it tolerates, what it corrects, and what it allows to persist. In these differences, we see evidence of both our fragility and our resilience. We are products of deep time and trial, a body that sings, stumbles, adapts, and survives. And now, having wandered through the anomalies of structure and the stories they whisper, we shift focus once more toward the great networks that connect us, not just to each other, but to the planet. From anatomy to ecology, we widen our lens to explore the web of life, a final meditation on our biological belonging. The anomalies and adaptations we have just explored remind us that every body is an unfinished draft, shaped by chance, refined by experience. In daily life, that draft is revised over and over, sometimes knowingly, more often in quiet automaticity. Classrooms and clinics are not the only places where anatomy is tested. Desks, playing fields, kitchens, and city streets become living laboratories in which posture, strain, nutrition, and emotion act as experimental variables. By noticing these trials, we can transform routine movements into sources of insight and care. Begin with the chair beneath you. Ergonomics, the science of designing tools and spaces to fit the human form, grew out of wartime aviation studies and now guides everything from keyboard angles to factory assembly lines. When a workstation aligns monitor height with eye level, supports the lumbar curve, and places wrists in neutral extension, muscle fatigue falls and concentration rises. Yet the modern world teems with poorly fitted seats, handheld screens, and hours of static gaze. The result is a quiet epidemic of tech neck, carpal tunnel syndrome, and lower back pain. Motion capture labs quantify how small deviations, 5 degrees of forward head tilt, a centimeter of shoulder protraction, multiplies cervical load by tens of kilograms. From this data emerge reminders to stand, stretch, and vary positions, simple interventions that recalibrate the study subject, who is also the scientist, the self. Sports arenas push the same principles to their physical extremes. In sports medicine, high-speed cameras, force plates, and electromyography reveal how milliseconds of asymmetry can tear a ligament or shave seconds from a sprint. An Olympic long jumper practices in a biomechanics suite, feedback lines glowing across hip and knee, while a weekend runner uses a smartphone app that tracks cadence and ground contact time via both pursue the same goal: adapt load to tissue capacity, letting bone remodel stronger and tendon align its collagen along vectors of stress. Knowledge loops from elite podiums back to community gyms, informing warm-up routines, shoe design, and the once radical notion that rest days are part of training. The repairing of damage when adaptation fails belongs to surgery, itself a centuries-long experiment in anatomical daring. Ancient trepanations proved the skull could be opened and life continue. Modern laparoscopy shows that organs can be stitched through keyholes. Robotic arms, guided by a surgeon seated at a console, tremor less than human fingers and allow suturing in spaces narrower than a grape. 3D printed bone scaffolds, modeled from CT scans, replace shattered jaws with millimeter precision. Yet, in every operating theater, the map is still the cadaveric atlas, drawn by Vesalius and updated by generations of donors whose silent generosity turns death into pedagogy. Such donations raise enduring ethical questions. Consent, cultural custom, and transparency determine whether a body may be dissected, plastinated, or digitally scanned. Medical students now supplement dissection with virtual reality cadavers, rotatable, layerable holograms derived from high-resolution imaging. These simulations spare tissue and allow infinite repetitions, but many educators argue they cannot replicate the haptic humility of lifting a real lung and feeling its weight. The decision to participate, whether as donor or learner, in reflection on dignity, gratitude, and the boundary between honoring and displaying the dead. Imaging itself has entered a new phase. Magnetic resonance, computed tomography, and ultrasound once delivered static snapshots. Today, AI-guided imaging stitches sequences into dynamic panoramas, tracking blood flow in real time, flagging subtle tumors invisible to the eye, and predicting fracture risk from trabecular patterns before any crack appears. Hospitals begin to create digital twins, full-body models, updated with each scan and lab test, enabling clinicians to simulate drug doses or surgical paths on a virtual patient who shares your anatomy molecule for molecule. The promise is tailored care. The peril is data saturation and privacy erosion. Who owns a twin that lives on a server farm? How secure is the heartbeat stored in code? Wearable technology pushes that question onto wrists and chests. Smartwatches record heart variability. Pulse oximeters track sleep apnea events, posture. Sensors vibrate when slouch creeps in. Athletes wrap inertial measurement units around ankles to monitor joint angles. Office workers sit on pressure mapping cushions that light up when sitting bones lean awry. Each device turns physiology into numbers, numbers into behavior change. Yet metrics can lure users into anxious self-surveillance, mistaking biological noise for crisis. Here, as in any lab, interpretation matters as much as measurement. The body is also a laboratory of empathy and justice. Ergonomic furniture is costly. Elite biomechanics labs serve a fraction of athletes. Advanced imaging clusters in wealthier nations. Meanwhile, garment workers crouch for 14-hour shifts, and miners inhale dust that darkens alveoli. Recognition of these disparities leads some researchers to design fold-out ultrasound units for rural clinics and to promote open-access motion analysis software that runs on a smartphone camera. Anatomy becomes not only knowledge, but leverage for fairness. Throughout these explorations, one theme endures: feedback. Whether through stretch receptors in muscle spindles, pressure sensors in shoe soles, or AI flagging an arrhythmia, information loops back to modify action. We are iterative creatures, cycling between trial and correction, damage and repair. To treat daily life as a living laboratory is to listen for these loops, respecting tissue limits, honoring rest, and welcoming adaptation. And so, at your next pause, feel the weight of your head over your spine, the rhythm of breath in ribs, the subtle shift of pressure beneath feet. Each sensation is data, and each adjustment rewrites the ongoing manuscript of your form. In classrooms of wood, steel, silicon, and flesh, anatomy translates into strategy, whether to reach farther, sit kinder, or mend more gently. From this vantage, the future beckons. Exoskeletons may lighten a caregiver's lift. Neural implants could rehearse stroke recovery in virtual space. Crowdsourced imaging might map disease before symptoms stir. Our bodies once static repositories of inheritance, are becoming participatory projects. In the soft closing of this section, hold that thought. We are poised on a threshold between what is and what could be. Let us step forward quietly into the closing pages of our journey toward a horizon where biology, technology, and imagination converge in careful, hopeful design. The journey has led us from the shy spark of a zygote to the full orchestration of organ systems. Now, at the edge of sleep, gather each part into a single breathing whole. Feel skin hold the world at arm's length, while bones rise like scaffolds beneath blood and lymph braid through tissue. Lungs sigh. Kidneys hush the internal tide. Even in stillness, cells divide, proteins fold, and genes repair slight slips, so waking may begin renewed. Yet tomorrow's body may not rely on patience alone. Gene editing scissors already silence faulty sequences. Stem cell bioreactors coax cartilage, liver, and myocardium to grow in glass. Titanium valves replace weary leaflets. Retinal chips translate photons for eyes gone dark. Enhancement whispers beside healing. Stronger tendons for athletes. Neural implants for memory. Pigments that shift with mood. Where therapy ends and upgrade begins is a frontier we now chart in real time. Some look deeper to creatures that regrow what we cannot. Salamanders rebuild limbs. Zebrafish mend hearts. Scientists parse their molecular playbooks, searching for switches long muted in mammals. If awakened, could a severed fingertip bud anew? Could spinal cords splice themselves whole? The prospect stirs hope and caution. For every advance, an ethical echo follows. When silicon threads laced with axons, does identity stretch or split? If embryos emerge free of hereditary blindness, will variety shrink or flourish? Justice must walk with discovery, ensuring access is broad and consent unquestioned. Regulation, transparency, and tradition all help keep astonishment humane. Parallel to wet biology, digital anatomy advances. High-field MRI, LiDAR-based posture maps, and glucose monitors stream data into digital twins, virtual replicas that age, train, and fall ill before we do. Surgeons practice incisions on holograms. Phone apps flag murmurs from whispered heart sounds. Pharmacists model drug interactions in silicon rather than liver. These mirrors may predict fracture, risk years ahead, or tailor rehabilitation hour by hour. Yet they raise dilemmas. Who secures the mirror? Who profits from its reflection? And how does one delete what should be forgotten? Anatomy's future is also ecological. Rising heat drives tropical pathogens north. Microplastics drift into blood. Smoke scars alveoli. Countermeasures will be biological, vaccines, engineered microbiomes, epigenetic shields, as much as mechanical. The body will adapt not over eons, but within decades, guided by insight and necessity. Amid such possibility, one constant abides: the quiet wonder of simply being alive, of housing awareness in tissue shaped by ocean tides and starlight. No implant can replace the first gasp of laughter or the ache of deep empathy. Technology refines, but experience remains stubbornly human. So, as eyelids grow heavy and thought drifts toward its own cinema, hold a final question like a seashell to the ear. What new symmetries, what hidden capacities, wait beneath the next dawn. Perhaps bones that knit without scars, or circuits that translate intent to distant hands. Perhaps subtler marvels, a heart rhythm shared across continents in real time, a breath filtered by living moss within the lung. For now, trust the body to its night shift. Osteoblasts will thicken struts where tomorrow's load will fall. Synapses will prune and strengthen, sorting memory from noise. Liver cells will file toxins away. Beneath the quilt of skin, a silent rehearsal readies you for one more day of gravity and chance. Rest in that knowledge. Your anatomy and its unfolding future belongs not only to textbooks or laboratories, but to the gentle rise and fall beneath your own ribs. When sunlight returns, may curiosity rise, too eager to explore the frontier that begins, unassuming, just under the skin.